The third and fourth concurrencies associated with a triangle are a little bit different in flavor from the first two. So the first two concurrencies we looked at were the concurrency of the perpendicular bisectors of a triangle, which we called the circumcenter and was the center of a circumscribed circle passing through the vertices of the triangle. And then on the second case, the concurrency of the angle bisectors, which we called the incenter, which was the center of a circle inscribed inside of the triangle that touched each one of its sides. The third and fourth concurrencies don't have circles associated with them that are special in any way, and yet they still represent concurrencies of a triplet of lines associated with a given triangle. In this example, we'll look at the concurrency associated with the altitudes of a triangle. So what's an altitude? We're again going to start with a definition of an altitude, and then also talk about a possible way to extend that definition and bend it in such a way that we'll be able to use it to prove concurrency later on. So an altitude of the triangle ABC, passing through the vertex C, so I'm choosing C here just randomly, is a line, we'll call it L, passing through C, that makes a right angle with the opposite side, AB. So sometimes we think of this as dropping a perpendicular from C to the other opposite side of the triangle AB. It's worth noting, by the way, that that point at which the altitude intersects the opposite side does not actually have to be between the two vertices of that side. It is in this triangle that's sketched, but if I sketch a different triangle, such as this one where the angle at B is obtuse, then you'll notice if we try to drop a perpendicular from C to AB, it's not actually going to hit the segment AB, but it will hit the extension of that segment into a line. So sometimes when you drop that perpendicular, it hits a place outside of the triangle, and that's okay. We still call that red vertical line in this example, we call that line L the altitude passing through C. So what's a consequence? Well, this is not a very surprising consequence, but it is an observation that we're going to use. That if I take a triangle and I double it, if I just take another copy of itself and I attach it to itself, I kind of flip the triangle over one of its sides, then I'm going to make a parallelogram out of that. So what do I mean? Well, let's suppose that I take this triangle, ABC, and I, again, drop the altitude from C down to AB. Then I'm going to think about that altitude as being the height of two different parallelograms, each of which has AB, the segment on the bottom, as its base. So one way to do that is to take the vertex A and flip it over to the opposite side, so that it meets a line which is parallel to AB. So I'm going to start this whole process by drawing a line passing through C, which is parallel to the opposite side, AB. We can do that because of Playfair's axiom, or the parallel postulate, in Euclidean geometry. So one parallelogram that we get in this process looks like this. It's caused by the fourth vertex D being as shown here, so that AC is one of the sides of this parallelogram, and BC is then a diagonal of that parallelogram. So there's one parallelogram that has a base of AB and has a height the same as the length of the altitude of this triangle. The other parallelogram that we can construct in this fashion is just created by flipping the vertex B over to that parallel line, thereby creating a vertex E, such that now ABCE is a parallelogram, and BC is one of the sides of that parallelogram, and now AC is a diagonal of that parallelogram. So there's a couple of parallelograms that we may be able to use some results that we know about parallelograms when it comes time to prove that the altitudes of a triangle are concurrent. One of the key observations there will be, what is the relationship between L, the altitude of our original triangle, and the line segment DE, which is this long side right here that we just constructed? Well, we know, by virtue of our blue line here being parallel to AB, and the altitude being perpendicular to AB, and this being Euclidean geometry, we also know that L is perpendicular to AB. So L is perpendicular, therefore, to the segment DE. What's a little less obvious is that it also cuts the segment DE in half. L, in fact, is going to be the perpendicular bisector of DE. And that's how we're going to get a hook into proving that the altitudes of the triangle ABC are concurrent. We're going to actually cast those altitudes as the perpendicular bisectors of a bigger triangle, which is a pretty nifty way to prove something. Okay, so what does the concurrency of the altitudes of a triangle look like? we'll take the altitude passing through A, perpendicular to BC, the altitude through B, perpendicular to AC, and the altitude through C, perpendicular to AB. Those three altitudes meet at a common point. They're concurrent at a point that we'll call H. That H is called the orthocenter of the triangle ABC. Notice that there's not a special circle associated with the orthocenter, the way that there was with the circumcenter and with the incenter. And yet this orthocenter still has an important role to play in the grand scheme of the concurrencies associated with a triangle.